Today we want to talk about the Hofmann product, famous chemist August Wilhelm Hofmann, not to be confused with another famous organic chemist, Albert Hofmann. Just a little chemistry trivia for everybody. So we want to talk about bulky bases in E2 eliminations and this Hofmann orientation. What other orientation have you learned about thus far? It starts with the letter Z. I believe is Russian. Close enough. I went online and I saw two pronunciations and they were each a little different. Zaitsev sounds close enough. One said Zaitsev, the other said Zaitsev. They're both on the internet, so they both must be true. If the substrate, that's the alkyl halide in E2 elimination, is prone to substitution, that means probably ones that aren't tertiary, like secondary or maybe primary, we can minimize the amount of substitution by using a bulky base. What about a bulky base is going to stop it from being a nucleophile? It's big and bulky and it can't get into the nucleus, to the atom, to the carbon atom. So a bulky base can accomplish dehydrohalogenation to produce a product that does not follow Zaitsev's rule. They form the Hofmann product, not to be confused with the Albert Hofmann product. So here's ethoxide, here's tetrabutyl oxide, and so this is bulky. It has 3 methyl groups around it. This is slender and non-bulky. So here is a secondary alkyl halide. This looks like 2-bromobutane. So all these hydrogens, notice they're adjacent to the carbon bearing the alkyl halide. So this base can come along, pull off this hydrogen, put the double bond right there, and that would be the Zaitsev's product. No, it wouldn't be. That'd be something else. That'd be the Hofmann product. So notice alkyl group, alkyl group, alkyl group. The Zaitsev's product's going to be more highly substituted, the double bond. So I'd be pulling off one of these hydrogens. So this can go in there, pull off that hydrogen. Those electrons jump down, and then you have a CH3 and a CH3. There's the CH3 and the CH3. But some of this comes along, pulls off this hydrogen, and you get 29% of this less substituted alkene. So this is called the Hofmann product, and we already studied Zaitsev's product. So this big bulky base has a harder time getting into here because it's running into this methyl and that methyl there, and so it runs into the end where it's not sterically hindered to pull off one of these protons, and we get this in the larger amount. So that's the Hofmann product. Bulky bases prefer to form the Hofmann product. A slender base, it's going to follow Zaitsev's product rule. And that rule in a sentence would be, when you can form more than one alkene, you form the one that is more highly substituted. This one we might say is tri-substituted. This one here is di-substituted. 2 alkyl groups versus 3 alkyl groups around the double bond. Yours and my favorite product, stereochemistry. The halide and the proton to be extracted must be anticoplanar. This orientation of 180 degrees to each other for the elimination to occur. So E2 means bimolecular, and a concerted event, meaning the base pulls off the hydrogen at the same time these electrons jump down, and at the same time the leaving group leaves, and you form your double bond there. So here's this 180 degree angle between this hydrogen and the halide. So you can see it's all in a plane, so all this can happen simultaneously. Now we can get everything in the same plane if we have this, but this eclipsed orientation doesn't happen as often due to the higher energy. So now we have this molecule here, and this stands for phenyl, a benzene ring. We study that in detail second semester. But right now, just realize this takes up quite a bit of room. It's a ring of 6 hydrogens and 6 carbons, or 6 hydrogens, a bunch of double bonds. It's going to have 5 hydrogens when it's bonded to something here. And if we look at the orientation of everything here, we should you should be able to look at this thing and predict this thing. So it comes out being what we might call trans or the E configuration. We'd give the benzene ring a higher priority than the methyl phenyl, a higher priority than the hydrogen. So we get kind of a trans alkene here. Most E2 reactions go through the anticoplanar transition state. This geometry is most apparent if we view the reaction with the alkyl halide in a Newman projection. So here these big bulky phenols are far apart from one another. Everything's nicely staggered. The hydrogen and the leaving group are all in the same plane. We can predict the orientation of the alkene. So now we get into the funness of realizing elimination and substitution are competing with each other. So the first thing you want to do is consider the strength of the nucleophile. So that table that had the weak to strong, you want to memorize most of that. And so the first thing you do is you look at the strength of the nucleophile, and that determines the order. Strong nucleophiles or bases promote bimolecular reactions. So E2 and SN2. If you have a weak nucleophile, E1 and SN1. Then you look at the alkyl halide, the substrate. Primary ones like to undergo substitute. Tertiary substrates cannot undergo bimolecular substitution. They're too sterically hindered. But we could get unimolecular substitution, and then we could have E1 or E2. They cannot undergo SN2. High temperatures favor elimination, and bulky bases aren't very good nucleophiles because they're sterically hindered. So they're not going to undergo a substitution. They're going to favor elimination. So here's a primary alkyl halide. This would be a strong nucleophile. So we predict bimolecular, and then we look at this and say primary alkyl halides, they don't have any problem with substitution. This thing has no trouble slamming into that carbon, having bromide leave, and it says we get 95% of this ether product. We substitute this OCH3 where that bromine was, so we get this ether. Almost entirely SN2. Now we have a secondary alkyl halide. We still have the strong base. A little harder for this thing to slam into here and for this thing to leave, but it still occurs. So here's the ether product, which we got from an SN2 reaction. Now this thing can come along here and pull a hydrogen off, and this would leave, putting the double bond there. So we'll see both an E2 product and an SN2 product. And under more heat, we might be able to favor one or the other. Previous slide said heat favored the alkene. So here's an absolute. Tertiary alkyl halides cannot undergo SN2 reaction. Remember our chapter 6. Here's a strong nucleophile. It's not going to do nucleophilic substitution. So what is it going to do? Notice all these hydrogens are equivalent. It's going to pull one of these off and form this isobutane here. Entirely E2 reaction. So the difficult substrates are secondary alkyl halides. So once again, if you know your strong and weak nucleophiles, you look at that first and you say it's either going to do this, SN1E1 or SN2E2. Strong nucleophiles with limited basicity favor SN2. Strong nucleophiles with limited basicity. So I'm thinking the nucleophile that had sulfur on it, like HSCH3, methyl sulfide. That would be a strong nucleophile, but very poor base. Alright, here we have secondary alkyl halide. We have two types of nucleophiles here. We have methoxide and we have methanol. So looking at this, we're going to predict E1 or SN1. Looking at this strength, we're going to predict E2 or SN2. And in the end, we're going to have the same type of products. We'll either have an ether with the substitution or an alkene with the elimination. So in each case, we have a reaction intermediate, a carbocation. Leaving group leaves, form the carbocation, and so the solvent either acts as a nucleophile, then there's the added step of deprotonating the intermediate, there's the substitution product, or the solvent acts as a base, extracts the proton, those electrons jump down, and we get the elimination product, the alkene. So here's a new concept. At the beginning of this chapter, we looked at how can you make an alkene, and it was by elimination reactions on alkyl halides. So here is another way to form an alcohol called dehydration of an alcohol. So here's an alcohol, and it says acid catalyst and some heat, and you form an alkene. So in 2 weeks, you get to do this in lab. And it says to use concentrated sulfuric or phosphoric acid and remove low boiling alkene as it forms due to Le Chatelier's principle. Is that what it says? So some poorly written equilibrium arrows, normally like the half arrows, this is a thing that's at equilibrium. So we typically use maybe an excess of a reactant. Of course, looks like just one reactant. But if we remove this as it forms, and this with hydrogen bonding, this is going to have a much higher boiling point than this. So we can distill this off as it forms, and most of these acids here act as dehydrating agents. They kind of tie up water. They really want water. So that's how we increase the yield of an alkene. And this is an E1 mechanism. Rearrangements can occur, and the reaction obeys Zaitsev's rule. What do you recall about leaving groups? What's a good leaving group? Polarizable, mainly a stable base. Is hydroxide a stable base? No, it wants a proton. How about water? Water is a nice stable base. Water is fairly neutral. So the whole point of that discussion, hydroxide never wants to grab these electrons and leave. You'd form hydroxide. But we can turn a hydroxyl group into a good leaving group if we protonate it. See, now it's protonated, and this happens pretty fast. And then once you have this situation, oxygen says, I'm electronegative, I can take my electrons and leave. And there's a nice leaving group. It's stable, it's not a strong base. If we try that with hydroxide, we'd have hydroxide hanging out. Nature doesn't like that. So there's the first two steps in an E1 mechanism. And once we have this carbocation, a base, could be water, could be our deprotonated catalyst. I sometimes like to write the mechanism. Comes by, grabs this proton, those electrons jump down, and there is your alkene. Or I like to point out, if we're using H2SO4 and there's some water around, we're going to have hydronium. Once this goes all the way to the end, we can imagine our HSO4 minus hanging out, counterbalancing this alkene. Other ways of getting alkenes is this catalytic cracking of alkanes. So probably over here at Sinclair, they do something like this. Just heat this thing up with some catalyst, break the chain in half. This might bring up a favorite topic of mine, degree elements of unsaturation. If I chop this in half, I'm going to need 2 more hydrogens. So unless they don't add hydrogen and just do it like this, there's no hydrogen to add. So we form an alkene. Chop this in half, you need 2 hydrogens to form 2 alkanes. So we form an alkane and an alkene. Another way to None of this is done in an academic lab. This is done on an industrial scale. Have you ever heard of green hydrogen? Nobody's heard of green hydrogen? Come on, don't you care about the environment? Fuel cells can burn hydrogen, but the cheapest source of hydrogen presently is to get it from petroleum products. Does that sound like a green thing? No, so hydrogen generated from electrolysis of water would be green. Using electricity from photovoltaic cells or hydroelectric, that'd be a good source of green hydrogen. What's the opposite of green? Black hydrogen. This would be some black, horrible hydrogen for the environment. But if you order up a cylinder of hydrogen gas, it was probably made from Sinclair down here with some method like this. Heat this thing up. And interesting things here. What is driving this reaction? Need a little more thermochemistry today. Notice it's endothermic. You already know that because we looked at the heats of hydrogenation of alkenes to alkanes to figure out how stable your alkane might be. So this is definitely at higher energy. Good reducing agent. These products are clearly at higher energy, and hence the endothermic change in enthalpy. But yet, if we heat up the temperature hot enough, this reaction spontaneously goes in the forward direction. It's because it's driven by the increase in entropy. This reaction has an unfavorable enthalpy. Products that are at a higher energy level than the reactant, but a favorable entropy change. Do it at a high temperature, we increase the entropy of the universe, and we can make our black hydrogen. That concludes our alkane chapter. And now you know the difference between two famous German chemists, August Hofmann and Albert Hofmann.